So there's, I think I was supposed to present yesterday, but I cannot arrive yesterday, so I have to present today. So the presentation switched today. And the project we're working on is working with the city of Austin. So we're using some, using the traffic monitor cameras to analyze those moving objects from the intersection. And my name is Rui Huang, actually. Rui Huang from Texas Advanced Computing Center at UT Austin. And the other research center is Center for Transportation Research, also at University of Texas Austin. And for Texas Advanced Computing Center, we're hosting several clusters, including the STEMP2, which is ranked number 12 around the world. So it has thousands of nodes equipped with Nice Landing from Intel, and the other is Skylake from Intel. And also equipped with GPU from NVIDIA. So I do those performance testing using these Nice Landing and Skylake and GPU units to test the performance of moving object recognitions using CNN, convolutional neural network. And in Austin, we have about 400 CCTVs, IP cameras. So for those green dots, they're still working, and for those red dots on the map, they're not working anymore. So you can see if you haven't been to Austin, you can see those clusters around the city centers. Those are actually pretty dense traffic cameras at the intersection. And those devices are not very well maintenance right now, and they install over decades and with different brands and specifications. When you look at those, when you search a specific intersections, you can see from the camera there are different resolutions, and sometimes they're not working, so lots of problems, and sometimes the angles is not actually pointing to the right direction. And also one problem for the image recognition, for the video recognition is that most cameras are automatically focused. Sometimes when there's during the evening, you cannot see anything. The zoom in, zoom out already happens very often, so you cannot see anything. You cannot detect any vehicles or pedestrian because it's like evening. The focus would be switch in and out, so it's really hard for us to detect anything during the evening. There's some common practice in the city of Austin. They're not recording all those videos at all, but when we try to do the video analysis, we have to ask them to record something for 24 hours or 48 hours at most. Sometimes they would not record those videos. They're just trying to ask somebody to monitor those screens to see whether there's some traffic accident or other things happens at the intersection. They're not recording those videos at all. And the project we're working on is to see how to automatically collect and estimate the key traffic matrix from those live videos. So we're trying to recognize those moving objects, including cars, trucks, pedestrian, and also those bus. So these kind of moving objects from the video. So we're trying to see what's the traffic volume at certain intersections, and also we want to see what's the speed of those movements, and also want to detect the direction of the movements, because it's kind of a very important matrix for checking those vehicles.
Does it detect bicycles also?
Yes, bicycle also. I didn't mention, but you can do that. So if you want to collect those video and save into a hard drive, it's really messy, and you cannot do any index and do any searching. So we're trying to, after we recognize those moving objects, we dump these moving objects into a database. Like, for example, if there's a car or bicycle, we're checking the cars as a number, like 1, when you first moving the traffic image. So I'll show you later. And then we can use the Hive QL to do the parallel search. It's faster than SQL because it's a parallel version of like Spark using underneath using Spark to do the search. I'll show you later. This is the general framework we're working on right now. So we also develop a web interface using Play framework, which is using almost like LinkedIn. They use Play framework, design the front end and back end. So when we analyze the traffic video, we use the deep learning, the convolutional neural network, which there's open source called ULO that you can use to detect those image or detect those video. After you're doing the object recognition, you can dump those recognizable objects into a database, or you can extract the background image from those videos. So that's the same. The labeling actually means when you have a picture, you can label those objects as car, vehicle, car and bus, pedestrian and bicycle. The tracking, that means there are several frames. Like for the video itself, it's like 60, or some camera has 60 frames per second, and some video has 30 frames per second. So the tracking actually checking if for example, if one bicycle coming into the video, and then coming into the first frame and then second frame, whether this vehicle is the same objects from the first frame. So that's the tracking we're working on right now. For the ULO, you only provide the labeling itself, so you can label a certain objects in an image, but it didn't provide the functionality of tracking. I will show you the video later. So for the big data processing, we use Spark and HiveQL. So it's very fast to do the searching and some querying. So as I mentioned, we use the ULOP. There is the theories under it is a convolutional neural network. So it evenly divided the image into grids. So for each grid, you can see here. I did not want to go into detail of this convolutional neural network. So finally, you would recognize a dog and a bicycle and some vehicle, like the final image. And some technical term here. So it has 9 convolution layers. So from here is convolution layers 1, including the max pooling, and then 9 layers here. And for this one is the RGB 3. There's like an array here. So not going into detail. Show you some interesting final result here. So from the image here, you can actually detect traffic line, but it does not guarantee it actually can recognize there's a red line or green line at that certain time of point, because it's too small and the resolution of the image is not very good. And also we detect a person here. And for the object checking, there's an algorithm here. Do you want to present, Weijia? And for the checking, we have a bounding box. For example, at the beginning frame, we did using the ULOP to recognize the objects using a bounding box, and we predict the next frame based on the trajectory of the bounding box, whether the location of the bounding box is at a certain location or not. Then we compare the previous frame with the predicted frame to see whether this object is the same objects from the previous frame. So that's basically the checking algorithms here. So we can see here is the 9022, that's the object type. Maybe the 9 is for the vehicle, for the car, or 2 is for the bicycle. And for the 4 numbers here is the minimum bounding box for the left, top left, and the lower right. So there's 4 numbers here, and the final one is the probability of whether the object is car or bicycle. So you can compare the previous frame for example, here is the previous frame, that's the current frame. So to do the checking. So that's the labeling performance results. You can see from the Skylake from Intel. At stamp P, we have about Skylake maybe 100 threads, hardware threads per node. And for the nice landing, we have about 270 something hardware thread per node. And for the performance plot here, we can tell the Skylake actually outperformed the nice landing pretty well. And also we compare the NVIDIA K40 and per P100. So we can see the quite similar performance with the P100 and Skylake. So the P100 is GPU and the Skylake is multi-core within one node. So that's the ideal performance and the Skylake performance, red line here, within one node. So that's the video. We're checking the vehicles and pedestrian. You can see the number is actually telling whether the vehicle is the same objects, starting from the previous frame to the next one. So you can see the number is coming out.
And so it's tracking speed as well, right?
You can calculate the speed based on the image.
Are you doing this in real time? You gave node counts, but can you process this in real time, or are you doing this as a batch job?
That's why if you go back to the previous slides, that's why we did the scalability study. The purpose is trying to see.
So those node counts are what you need in order to do it in real time?
Exactly.
Okay, that's what I was
So in the result we're showing here, it's all batch processing. But if we want to do it in real time, we need
That's what you have to do. And does it scale? It does scale adequately that you could do it in real time.
Yes.
And you say you're pre-training with a code data set. What is the code data set?
It's a large collection of image. So actually training the model, telling whether it's a flower or other like dog, a cat.
Specifically recognized vehicles and pedestrians. So
Yes.
do you train specifically for the target objects that you are trying to identify?
We don't need to train specific for the car or pedestrian because the model is already trained for that kind of purpose. Not for this kind of purpose, but for a general purpose. You also can detect cats, dogs.
Also, you are actually not training it again. You have
No.
previously trained
Yes.
a layer. And
Yes, there's a pre-trained model in the,
training on
yeah.
the top layers.
yes, the pre-trained model in Europe.
So with that context, how many objects is it capable of recognizing with the Cocos model?
Do you remember how many objects? Maybe.
Dog, cat, car, truck.
Maybe hundreds of dollars.
Maybe lots of.
I think the Coco dataset has an 80 class.
Maybe
So
classes.
80 different objects, but for the purpose of our study, we're actually limiting it to 10 class as relevant to car, truck, pedestrian, bicycles.
And does it?
This should be about 100
Leading to
class.
a question here that I was trying to understand, which is it scalable by the number of objects you're recognizing, or does it slow down as you add objects? In other words, if you only recognize people and cars and bikes, does it run faster than if you recognize people, cars and bikes and dogs?
It doesn't affect that much.
It doesn't.
Yeah, I don't think. Yeah.
Computation is just one computation regardless how much. Well, it does a little bit if you have more label object class,
Yeah, more
it's
classes.
taking more time, but it's not that significant. It does affect accuracy, how accurately you can recognize each
pedestrian is harder to recognize than cars, actually.
Yeah,
Yeah.
but that's a problem. I mean, that's,
It's interesting that it's not persistent. I mean, right, you've got some of those pedestrians we picked up,
right,
but then they disappear,
right.
right? You'd think it would find it, once it knows there's a pedestrian there, it would.
Because we have a criteria, at least 5 frame, continuous 5 frame identified as pedestrian, then we draw the bounding box for that pedestrian. If there's no continuous 5 frame, then we lost the bounding box.
For the labeling in this video, it's we only label the one that's continue moving. So that's why you see the car parked in the side. We basically do not label them as well.
Right,
So
but
the
that
same
person
thing with the
just,
pedestrian there. If it's not moving or because the moving for the pedestrian is very small range, so sometimes we considering the manifestation as well. So they are not being picked up. If you see later if the pedestrian starts to moving in the straight line, it will be picking up at the pedestrian.
right, but if you back up, that person who walks straight up the
Right. So
the
the
sidewalk disappears after it passes the J sign.
right. So
Yeah.
walk
You could stop right there.
From the camera is another problem.
Yeah.
Because eventually we get less pixels per
Yeah,
pedestrian,
it's
so
not
it's
enough to
harder
trigger.
So basically we can, for pedestrian, we can only start recognizing them only after they are like over the lower half of the screen.
Got it.
So actually this is the same thing with the cars. So if you see the cars in the street in the back, we can now consider recognize them as well, not just the per pixel each car just use those there.
How does multiple video sensors affect this kind of recognition algorithm? Is it possible for you to map points in a 3-dimensional space and take a look at? In some cases, there would be something hidden here from the view of this camera that could be seen from another camera, but algorithmically, that just lends some additional richness to the field of objects to identify. So some sensors exist like that. There's a gadget that sees things in 3 dimensions and in real time does that. But it seems to me that sensor technology is so inexpensive, cameras are so inexpensive, that being able to see around the corner or see what's happening and bring those 2 data sets together could take a step towards a predictive analysis, right? So because you don't want somebody to step out into this motion field, but if they're hidden behind that alleyway,
Yeah.
they're going to walk into this. Have you guys considered how that might evolve?
We only have very limited in terms of sensors. We can use some of the data we can have access to. So it's harder for us to do that type of studies here. And even for the other thing we try is we're trying to study multiple cameras at the same time. But we do not really have
Yeah.
triangulate and stuff like that, you know, and,
It's not very easy to
right.
combine information from two different cameras because you also have to know the exact coordinate of that location to see at also exact timestamp at that certain point to recognize.
Is it pulling in a GPS signal as well?
No, no GPS, no.
Identification process is based on a template and learning already. The amount of CPU cycles that you need in order to do this is fairly low.
Right.
So that makes the cost of deployment relatively low too, which is obviously attractive. But if we want to move into some three-dimensional space where we work at multiple of these, it may require some additional horsepower that does some real-time analysis and some heavy lifting. And that might be expensive. So if you want to look at a domain and say, this is a 2-block domain and all of the potential risk intersections there, you may have multiple cameras feeding a three-dimensional image that then trains something in real time potentially. Right? And then you look at GPUs and potentially multi-$1,000.
Sure. So what is the exact application for this? Is this designed to just gauge traffic and road usage, or is this designed for emergency or predictive against, road fatalities or pedestrian fatalities or anything?
So our initial goal is to study the traffic, as traffic statistics, traffic volumes, how people using, how cars using the road.
Okay.
So it's not even for the purpose of the emergency stuff.
Got it. Okay.
Yeah, if you dealing with this access cross line, you see we have access layers where we accessing the first kind of label. So it's initial goal is also not for the real time incident detection, but also for the after we collect the summary in the video, how we can let the decision makers know what's achieved in the road.
Sure. Got it. That makes more sense.
There are several private networks, so we have to do some port forwarding through this private network because there's firewalls for each network. So I'll skip this one, and that's basically some steps we're doing, collecting the video from City of Austin using our virtual machine at Texas Advanced Computing Center. So we do some technical steps here, so doing the port forwarding process to record the videos that require less CPU resource and no local storage requirement to the City of Austin virtual machine. So we can do multiple port forwardings for multiple traffic cameras. So that's basically the same video streamings.
So a question on policy and sort of a guideline for this. Is it explicitly defined in the documentation around the system or in this example of what data gets collected, what private information is collected? So is anyone currently looking at this general data protection regulation and then doing some explicit, because we in the data supercluster we're looking for white papers, examples of licensing, examples of community engagement that describe why not to worry about the fact that a sensor like this is being deployed. In many cases, citizens just don't want to be observed. They certainly don't want to be observed to the level that they're identified.
I think those videos are very low resolution, and also these cameras information also open to public. You can go to the City of Austin website. You can actually view certain cameras content right now.
So it's already open.
Yeah, it's open to public.
So the general rule in Austin is if you're out in the streets, you're able to be photographed and viewed and the photographs usable.
That sounds
Yeah.
Actually, that's the fact, right? I think that you can tell people about these spaces.
It's very, very low resolution, so you cannot tell who the people is at the video.
Are those policies made at the city level, or is that a national policy?
It's a really good question.
It's a great policy. It's a great question.
I don't know if cities, but certainly national policy, I mean, most of know, there is the sort of law that if you're in public, you can be photographed without your consent.
There's no expectation of privacy
Yeah.
Right.
in public.
But I think cities are setting sort of an expectation for citizen privacy at this point, which is vague.
And the sticky portion, the sticky wicket, if you would, is that it isn't just the image there, but somebody may be carrying a phone that emits a GPS signal or Bluetooth locator information, and suddenly that person's ID is there. And then they can coordinate the image, time of day, person's actual location, and they have identified that individual uniquely. So that's an expectation of privacy that's sort of out of the realm of a photographer to the picture.
Well, the other side, for example, that you see a lot of the Facebook videos coming up, and for example, the United flight incidents, for example, somebody took a video of that whole incident and put it on the website. That whoever did, I don't think he got sued because they identified the guards and police in the picture. So it's just that when you are in public, the assumption is somebody will take a picture or video and put it on that picture.
What if this is a global product, for example, or then do you have to, I mean, if this is taken to UK with new GDPR laws or whatever, do you have to then make sure that the information is?
Yeah, so so I have no idea about the policy stuff on
Yeah.
Nixon and this
Yeah,
policy.
yeah.
In China, it's very different. They
Yeah.
have a camera everywhere,
Yeah.
like of them. So one of the things why we are doing this project is actually we don't really care about the policy for our website.
Sure, yeah.
What we want to do is we want to use the recognition so we can start working with into a sort of anonymous object. So
Yeah.
we can working into car, into pedestrians, we don't really need safety.
Got it.
We don't need people to safety.
Okay.
So these two slides exactly show that accountability
Right.
where we can process it, we will have a label green there, we can process the background image, and we also have a sort of database where we only store the objects and car ID number 1, car ID number 2. So that information will be enough for traffic.
What the purpose is.
To study traffic volume and pedestrian.
I guess I was asking kind of a higher question for these types of applications.
In a way, we think this is at least a approach that we can get away from the privacy
Sure.
issue.
No, right.
We really need to save the paradise of the review.
Yeah.
People can only save the recommended object in terms of reconstruct what people use.
Yeah, makes sense. Makes sense.
It's a sidebar here, but I think the GDPR says that if you're a citizen, you can request of the company who's collecting data, do they have any data on you?
Yes.
And what is it? What's the purpose? So that's an empowerment, but
And then
does
could
it
you please
require,
remove it?
it doesn't, I don't think it would require a cameraman, for example, or someone else that's putting up something
We'll see.
to say,
What the rest of the cases are.
it's sort of a lot less.
Okay. So the specific use case is for pedestrian activities. We want to know how pedestrians use the crosswalk or not. So we identify some locations, 3 locations here at the North Lama Boulevard. Actually, there's a bus route around that road. So we want to see whether the pedestrian use the crosswalk or just cross the street without any crosswalk. So basically our purpose. So we can aggregate those pedestrians based on their appearance on the video. So that's the one image. For different cars, is showing the different time during the days for the pedestrians, for those clusters within a location. That means the pedestrians stay at location or stay at the location for a long time, or clusters of different pedestrians across at that certain point. And we also link the pedestrians' trajectories into line to see where those pedestrians across streets at certain
So like in this
location.
You see this is a summary of
Right.
the basically one page video
Sure.
of people activity and things, but we don't really need to show the people there.
Yeah, so there's like a summary of the abstraction of the pedestrians' behavior across the streets.
There is actually a people back to the bus stops on the right in the middle left part out there, so that's why there's like
different time during the day.
So
Different time during the day.
different time during the day?
Yeah.
Thank you.
So there's another image. There's a,
So they're not very big on crosswalks.
yeah. So probably there's a park, right? There's a park nearby, so people just cross the street without any.
They need a crosswalk.
Exactly.
They need a bridge.
So there's like a policy recommendation. We suggest maybe put a traffic line or stop sign or
Yeah.
something over there.
If you can open the Google map, it's actually very interesting for this one because on the right there's a trail, so people go jogging, running there. And it's not showing this picture, but more further down, there's actually a bus stop there as well. And on the right side is actually a big apartment complex. So that's explains why there's not enough
Really need the
It's
crosswalk.
the crosswalk.
Yeah.
It's one of those places where you can have one of those high accident rates.
Exactly.
So I think that's a summary of the case study. So using the recognition, we need big data processing powers. So HPC is kind of like a big facility we have to use, powerful facility, and we'll coordinate with the city of Austin for more camera access over time, and we want to do like some real-time processing using the multiple cameras with high-performance clusters. Also, we enable to do some content-based search and analysis of the videos, such as the database we build for the checking the car or pedestrians with the checking numbers. So we can analyze the data using that kind of database. So I think that's what we did, and using deep learning and big data processing, using the high performance computing, have the high effectiveness for deep learning. So, any questions?
Do you think there's any possibility of